All right, I'm just gonna kick it off. My name's Joellen Russell. I'm a Scripps grad from back in the 90s. And this is Climate in the Deep Blue Sea, otherwise known as How I Fell in Love with Scripps, and am still working with most of you. So I always start here. It's our pale blue dot. We already talked about astrobio and how important this is, but of course this is Carl Sagan called up NASA and said, hey, tell the Voyager probe to turn around and take a picture of home. And it's blue, and it's the only blue planet we've ever found. Kepler mission tells us there are thousands of other planets orbiting other suns, but the only one we've ever found that is blue so far. I know, Jess says we're gonna find it, but there aren't any yet. And it's blue, 72% of the Earth's surface, and I have to tell this often to my Arizona students because, of course, we're landlocked, and they don't understand necessarily, although I have now convinced our governor of why it's so important that we do ocean science. So if you like your weather forecast, and I'm quoting McLean or Rick or anybody at NOAA these days, this is FV3. Everybody looks at this and says, what lovely satellite data you have, but it is not satellite data. This is math and supercomputers. This is the prediction science that basically tells everybody when to get out of the way of a hurricane or a tornado or the next big flood, or in my case, massive drought. Did you know we've had ½ an inch of rain in Tucson since October? Yeah, it's the driest it's ever been on record since 1895. This is it. This is as dry as it gets. And last summer, of course, we had record hot. So I used to think when I was very young, sitting here, this didn't exist back when I was here, that we would eventually get so good at weather modeling that we would do climate with weather models. And that's not what happened. We got so good at climate models. In 2016, there was a bake-off at NOAA, and the Weather Service model was put up against GFDL's FV3. And FV3 won. So now a coupled ocean atmosphere climate model is what they use for our weather forecasts, except for Marty, because he does it different, but they're very, very good, and I enjoy his atmospheric rivers. But I'll just point out that the University of Arizona is the only university ever in the history of the universe to run the IPCC DEC, the Intergovernmental Panel on Climate Change's Couple Model Intercomparison Project. We ran the DEC. We did not, of course, come anywhere near. We're using an older version of the GFDL model. And we did not win the beauty contest. We were about 64th percentile, which is, we beat the Chinese, we beat the Germans, we beat 2 of the French models, but we did not beat, we beat a couple of the NASA models. But it's one of those things where we start with this incredible curve, that Dave started. I miss him too, although it's nice to see Keeling 2.0 here. And there are incredibly important things going on with our planet. You might have noticed that it's getting hot in here, but in Arizona, we have really noticed that it's getting hot in here. And this is ERBE, Earth's Radiation Budget Experiment. It looks a series of satellites that look out at the sun and in at the Earth and say about the same is coming in, but less is getting out. And you can see all the time that it's above 0, this is basically accumulating within the Earth system heat. And that heat, that radiative forcing, everybody's like, what about methane? I'm like, I don't care. I 100% don't care. Look at this. The difference in methane is not that big. The difference in carbon is catastrophic. It's insanely important. This is the radiative forcing from the annual greenhouse gas index. It's a big deal. We are now, that was 2020, 2023, very, very hot. And we were like, oh, look at that El Nino pop-up. We expected that. Okay, 2024, La Nina. And it popped up even higher. Everybody's like, what is going on? It shouldn't be popping up even higher during a La Nina year. This is crazy. And yet, this is what it did. So 2023 was the hottest year by a lot. But 2024 beat it. No, I'm getting to the ocean part. I am. 2 seconds. And this is what it looks like for driest. This is the difference between now and what was normal 10 years ago. That shifting baseline is killing us here in the Southwest. Yeah, that's us. We're out there in Arizona, and you guys are over here, also dry. So what we need here, at least in Arizona or anywhere in the Southwest, is we need to know more about our heat waves, because we had over 900 people die due to heat-related illnesses in Maricopa County in Arizona alone. One county, 900 people. We don't talk about this. We talk about hurricane deaths. We don't talk about the 900 people who are either unhoused, addicts, or like our diabetic friend who went out to hang his laundry out at lunch, fainted because of the heat, and his wife didn't get home, bringing the groceries home in time, and he died. Just because he fainted because he was out doing his laundry, because it was too damn hot. It's crazy how bad it is. And of course, this is an ocean problem. Everybody knows this, right? It's all about how much ocean mixing there is. That little tiny pink line in the bottom, that's the atmospheric heat accumulation. It's near zero. It's less than 3%. And I love this new warming stripes. This was put together by Hawkins and Rick Williams. And if you look at the bottom, here's the deep ocean warming over time from 1960 to 2024. Above that is the upper ocean. Above that is the troposphere. And above that, the stratosphere. And this is incredibly important. That cooling stratosphere, that warming troposphere, is creating stronger winds. Changing winds means changing mixing in the ocean. Changing mixing means changing climate. I did this work back in the day at GFDL with Robbie Togweiler, and this is the day we figured out what we thought was going on, and that poleward shifting westerlies happens in every warming climate. And we didn't just do it on Earth. Eventually, I went and did it with a grad student, and we did it on Titan. We're doing the Milankovitch cycles of Titan. It turns out it works on any planet with a liquid or with liquid and atmosphere. And this mixing change associated, just so you know, that is my advisor, Andrew Dixon, and that was my advisor in undergrad at Harvard, Jim Butler, and this is us having dinner in Del Mar. I got the picture back in 1994. Just so you know, my Scripps roots are pretty old. And that transient climate response is how much mixing there is in the ocean. And it absolutely changes. It's about half the rate of warming that you would see with equilibrium climate sensitivity. So we're comparing those two, equilibrium versus transient. The transient's what you, me, and our great-grandkids are gonna live through, and it's all about ocean mixing. It's all about ocean mixing, more than even our emission scenario. This is what happens if you warm the ocean, and this is Norfolk, our largest naval base, not that San Diego is small. This is what is happening with nuisance flooding. You can see up, 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 up she goes. It's bleaching on the Great Barrier Reef and worldwide. It's melting back of the Arctic sea ice, and how we're gonna do coupled ocean atmosphere sea ice prediction. Now, how well do you think a statistical model is going to do for sea ice prediction given the change in warming in both the ocean, the atmosphere, and the change in the winds? It isn't. Those statistics from 5 years ago, 10 years ago with that baseline are no good for looking at what's going on today. It isn't gonna work. And this, of course, is worldwide shipping. I use this because my students don't generally, they step up at the ocean. It's kind of empty. I'm like, or full of people and ships and critters. It's amazing. Would you like to predict, our changing crab fishery as well? These are spectacular change bearing down on us worldwide. 72% of the global planet is ocean. And what do we have? AGU tells me we have roughly 6,000 PhD level oceanographers in the world, right? 60,000 meteorologists, 600,000 geologists, 6,000 oceanographers, a big fraction of which are right here at Scripps, right? Right here. And it's the only, so you're responsible for 93% of the energy imbalance of the planet. You're responsible for 1 out of every 4 carbon molecules that comes out of anybody's tailpipe anywhere in the world, and you're responsible for what happens next for everyone. Everyone. All 8 billion plus people on the planet depend on what you produce. This, I know Rick did a great job of setting the stage here, but I have a 14-year-old and an 18-year-old, and I am terrified. This is actually the law of the land. The Clean Air Act does in fact cover carbon dioxide as a pollutant. This endangerment finding, they cited one brief. It was the scientist brief, the amicus brief, and I'm one of these, so I'm sure I'm on some list somewhere because of course they're now attacking that endangerment finding again this year, and we have rewritten the brief, and those of us who are still alive, where we've lost a few. And this is our global carbon total budget. I love it because it gets from, so everybody's like, we're gonna solve this with agriculture. I'm like, well, at 11%, no, you're not. It's really going to have to be in the other human sectors like heat, electricity, manufacturing, transportation, et cetera. Most folks don't know that the United States has cut more than 20% off its total emissions since 2007. That Massachusetts versus EPA ruling came out in April of 2007, and our peak emissions in the United States was in August of 2007. It's been coming down ever since. And we are, in fact, dropping faster than any other country on the planet. I know that seems odd, like, hey, aren't you guys the bad guys with those big emissions? But we are actually cutting our emissions quickly. If we stay on track, and so far we have, we will not make 50% cuts by 2030, which was the goal if we were under the Paris Agreement. We're gonna make it by 2032. Oh, boo, we missed it by 2 whole years, wah. So what can we do as scientists to actually back this up? And David and Jess are gonna say, David's gonna tell us what we should be doing, and Jess is gonna tell us what we're actually doing, which is so cool. So here's, as oceanographers, if we know the emissions, and we think we know the land use, and we don't know the vegetation, but we know the atmosphere and the ocean, thank you, Keelings, what could we do to reduce those uncertainties? And of course, we need to know this really well for MRV, for our marine carbon dioxide removal. So my worry about this is always not what is actually happening today, but what will happen with the change in the mixing. Bigger winds means more upwelling, means more mixing to deeper. And I like this orange peel version of the ocean because I'm a Southern Ocean nut. My first cruise in the winter in the Southern Ocean, you know, with oxygen electrodes that were brand new, and I only had 4 of them, and I was on my last electrode for about 3 weeks. Like the entire time sleeping in a beanbag going, please, dear God, don't let me break this last one. Andrew will kill me. But it's where I figured out that, in fact, the surface ocean in the winter in the Southern Ocean is undersaturated. Absolutely undersaturated the entire time, which given the wind speeds and velocities and how quickly oxygen equilibrates in the surface ocean seemed insane. And I wrote to Andrew, and I still have this email. I wrote to him and I said, Andrew, I have done the replicates. I have done everything I could do to try and figure out what's going on. And he said, trust your data. And so I've been obsessed trying to get this data forevermore. 50% of the carbon dioxide in the ocean, 75% of the heat, and doing it in ridiculous, awful, terrible conditions, particularly in the winter. All the white space on an oceanographer's plot, this is what Argo did for us. It's extraordinary. It changed the world, and most people don't even know about it. So we came along behind, you know, Global Array in Argo in 2006, I want to say, and we got SOCOM going for biogeochemically censored floats in 2014. And this is just my student, Becky Beedling, Lynn Talley, she was on my committee and is still my mentor, she got Becky on a ship, and Becky came back. She's a modeler. She's a professor now at Temple University, and she's like, yeah, I'm not going again. But there she was deploying BGC Argo floats for SOCOM, and this was our first 2014 to 2024. And of course, it's not, oh, and this is Hannah Zanowski teaching her big oceanography class. She sent me this picture because my oceanography class has this fall it had 503 students in it. And she says, it's not as big as yours yet. Which is fantastic. So, of course, this is Allison Gray, who started as a postdoc at UW and is now a professor there. And this is how we do real-time, near real-time carbon. It is amazing. And it was so amazing, we made it to the front page of the New York Times with a full digital interactive based on our GFDL collaborative modeling and the float data, which front page above the fold, and check it out. There is BGC Argo. We have a lot, so much to be thankful to Scripps for. One of those is pioneering this incredible array, which allows us to do carbon, oxygen, nitrate, well, I'll say pH, not carbon, in near real time, worldwide, which is a feat. Most, unfortunately, 90% plus of these floats are American. Not like Argo, which is closer to 50-50. not that close to 50-50 these days. And there we are, Lynn and I'm in the pink scarf there in the middle. And this is what, instead of doing those oxygen measurements with an electrode in the middle of the winter by myself, scared to death, instead, this is the oxygen data being reported back from all those incredible floats. And that undersaturation near the surface that I thought was so weird and I couldn't understand, was it going to happen every winter? Was it going to happen all around the Southern Ocean? How long would it last? How much mixing and upwelling was there? Now we can see it. We can actually see it in real time. I cannot tell you how much the world has changed since I was here with all of you. So these growing winds are a response to this incredible thermal wind change. If I make my students do this on the back of the envelope for their comps, because if you can see how much colder the stratosphere is, how much warmer the troposphere is, you can calculate how much higher the winds should be. Increase the gradient, increase the winds. And those winds are higher just about everywhere, especially in the very fastest winds, especially in the Southern Ocean. And it's driving all kinds of weird things, including changes in atmospheric rivers. This is the total precipitable water in the atmosphere. This is the mixed layer depth. And I know the IPCC in 2000 said, hey, we're going to see stratification worldwide with shallower mixed layers. That's not what happened. 25 years later, that is not what's going on. And part of the reason we missed it is because we're undersampling, and I'm going to give a big shout out here. These are the Southern Ocean wind storms are undersampled both in all 4 of the major reanalyses. They just get it. In all winds south of 40, it's almost 30% too low. Too low because we don't have enough measurements. And I'm going to put a big pitch in here for Sarah Gillies' Odyssey. I hope this goes. I know it's a mess on the federal level, but it would be awesome, and it's something we really need. But supercomputers and climate models, float data for initial conditions, and fantastic satellite coverage to get the real deal. Because we don't want to just have a prediction, we want to have a prediction based on, and then a cross-check to make sure we're getting it right, to improve those forecasts and predictions that we're making so that we can actually see what's next for every one of the 8 billion. Right? It's absolutely essential. And if we understand and are good at it, we could do this. So what I'm worried about is if I add 20% to Matt Masloff's amazing BSAUCY, where he's got this biogeochemical data assimilation, if I add 20% winds to this, I end up degassing out of the Southern Ocean as a net product. I know, this is bad. So I wanted to see if we could apply this. I did a Fulbright at NIWA in New Zealand, and they actually have a real-time measurement of their emissions. They actually measure New Zealand's impact in the atmosphere. Problem is, they come up with half of what they knew they were emitting. So where did it go? Well, they checked the cows, and they checked the grass, and they checked the forests, and they checked the rivers, and they did. Luckily, the first place we deployed floats for these BGC floats was off New Zealand. So what we found when we actually did use BSAUCY in a reanalysis of the last 10 years of data is that, in fact, we have a real-time record of the release and uptake of the New Zealand exclusive economic zone, and it is 0.83 correlated with the change in the missing carbon for New Zealand. So we're trying to do this now. Okay, one last little thing is we write lots of cool papers that come out in big journals. We teach a metric ton. We have hundreds and hundreds, but we also I have a side hustle with Katherine Hayhoe called Science Moms. And these are climate scientists who are also moms and who have been doing outreach to regular folk, starting with moms, but also aunties and uncles and dads and everybody else to try and get everybody on the same page with
To my smoochy babies, Maeve and Joseph. I loved you before you were born. Even as I chose my career as a climate scientist, the joy and wonder that growing up on the Chukchi Sea gave me, I am determined to give you. Even as the Tucson summers get longer, the saguaros wilt in the heat, as we get up earlier and earlier to hike, and we depend more on our AC, I chose this life to help build a better world for you. I hope when you're grown that you'll forgive me for being the tired mama, the obsessed with the new data mama, because the climate is changing so fast and will affect your world so much that I've had to become your gladiator science mama so I can fight every day for you.
So we've done a bunch of these now, these little snips and videos. They should be able to be watched in your pickup line while waiting for your kid to get out of school or drop off, etc.
What's the plan?
And we actually had a Super Bowl ad. Thank you to some of our big donors like Mackenzie Scott Bezos. We don't ask anybody for money. It's totally nonprofit, nonpartisan, and because we don't have to, because the donors have been the big ones have been so generous. And we had a Super Bowl ad, and the New York Times rated us number 8. You know, we could not beat the Clydesdales, but we did pretty good for a climate change ad. So we're trying to get the word out even under these conditions. We're going to keep building out that carbon observing prediction system, completing implementation of near real-time carbon accounting for the ocean, and we're going to publish the top 10 economies' monthly carbon bill, basically, and try to, you know, save the planet or at least bend that curve. We can do it. Thank you. Lynn, yay! Jess, you're up. Here, let me.
Yeah, we're going to have a panel conversation right after. And yes, I've been instructed by my boss to make a brief introduction. Our next speaker, Jess Adkins, who is a former colleague of mine when he was actually in the exciting world of paleoscience, and he gave that all up for what you're going to hear about today. And I remember sort of the moment that I learned of Jess's pursuits when another of our paleoclimate colleagues here at Scripps came in and said, all excited, Jess is going to save the world. So this is in keeping with what Joellen just alluded to. And so, Jess, take it away.
Thank you, Chris. Thank you, Joellen, and pre-thanks to David. I think it's a really fun group that you guys have brought here. So thank you, David and Victor, for pulling us all together. Yeah, I'm going to try to tell you a quick, which I'm not so good at, story about basic science leading to applied science. And this has not been touched on in Margaret's career very much, but Margaret actually left the National Science Foundation to go be part of CLIMOS, one of the very early applied problem solvers. And I've been thinking a lot about how we measure impact. I would love to talk to folks about this over coffee or over dinner on how we might think differently about numbers of papers or amount of money as ways of judging impact. But I'm going to try to tell you a little bit about basic science leading to decarbonizing shipping. This picture in the background is a moment in shipping. Every ship that has its GPS turned on is in this picture, at least for this part of the Earth. And I think you can see all sorts of super cool things here. This is 3% of global emissions of CO2. It's about a gigaton a year. We move a lot of stuff because we buy a lot of stuff, and it's got to come from somewhere. Okay. I can't come to Scripps and not show this. This sort of goes without saying. Thank you to the whole Keeling family, of course. And I think one of the amazing things about this is how hard it is to keep time series going. It's what we need leadership at places like Scripps for, because I think that this family has struggled very hard to make this available to us in such a key way. It is not the first famous Keeling plot, though. This is now CO2 concentration on the x-axis and the isotopic composition of C13. And I'd like to point out that this paper was published by David when he was working at Caltech, my current employer, or at least 20% employer. And so the Keeling plots were rolling out even before he got here and started making the famous ones. There's some apocryphal stories that Sam Epstein actually told me about David taking the evacuated flasks and going up to the Inyo and going up to Mount Wilson you're trying to understand the amount of respiration that's going on in the forest. And of course, he's respiring the whole time. And so what he would do was hold his breath and sprint into the wind in the forest and then open up the flask as he went as a way to try to not contaminate his sample. I think that's great. Okay. I do have these paleoclimate routes, so just to put into perspective that measured CO2 rise, this is now 800,000 years of climate. We've seen some wiggles like this before. Blue is the PCO2 record from the Antarctic ice cores. Red is the proxy for temperature in the isotopes of the ice. I can't make this line thin enough. That is the CO2 record put on top. I don't think we have to have climate models, though I love Jo Ellen for having them, to recognize just from the data that we're conducting an experiment of unprecedented magnitude and rate on our climate system, and we don't know the outcome. So we also know exactly where it's coming from. These are two of the same data sets. It's the rate on top and the integral down below since 1800 of what the source of CO2 is to the atmosphere. The blue line, there's all sorts of fascinating inferences in here. The blue line, the thick blue line is the sum, and you can see at first the Industrial Revolution comes from coal, and then as the American era starts up there post-World War II, that comes from liquid fuels, that comes right from the gasoline. And I think one thing that we should make sure we understand, it's a demonstrable good for humanity that we're using fossil fuels, right? That is the growth of the American economy there. That is a lot of people coming out of poverty. But we have to clean up the garbage. And we haven't been cleaning up the garbage, and we've been poisoning the commons as we go. One thing, though, to bring about, right, to make sure we understand, is that the climate doesn't actually care about that number very much. The climate cares about the sum, right? The climate cares about the total amount of CO2 that we put up there. And it doesn't really care if we call it CCS or CDR, right? Whether we talk about it from point sources or whether we're going to deal at point sources or take it out of the atmosphere. It's really just the running sum. That's a self-serving comment for Calcarea. So can we do it? Can we electrify everything and keep ourselves from emitting CO2? It's absolutely an important goal. We must try to do this. We can't only try to deal with our carbon problem by taking CO2 out of the atmosphere. It will not work. We will heat up too much, and there are too many disasters in the paleoclimate record for us to ignore them. However, I don't think we can ignore taking CO2 out of the atmosphere anymore. This is the US EPA back when they used to publish data, and you could go get it. The US economy, this is not the world, this is just the US economy divided up for its greenhouse gas emissions amongst different sectors. It's, of course, the heart of the problem is that there's not just one place we can go and try to solve it there. It's really across the entire economy. And embedded in here are things like process emissions in steel and cement. Even if we were to electrify steel and cement, they would still put CO2 out because they're converting limestone into lime. And then aviation and marine transportation are very hard to electrify. They're probably going to emit a bunch of CO2. And I don't know how to do this. There are people out there who are way better at this than I am. But something like 15% of our current emissions are probably still going to be with us once we get to the job of electrifying everything. The biggest uncertainty there is probably this adoption curve problem, right? That we're doing all the easy stuff first. Turns out EVs are super easy. It's all of it's like heat. What are we going to do about industrial heat? That maybe we're going to end up wanting to emit that to the atmosphere and then take it up in some other way. And so, what are we going to do? Well, we heard the long-term, the millions and millions of years timescale version this morning about what the Earth does about this. It's silicate weathering. It's CO2 plus the base in silicate rocks, making the neutral salts of bicarbonate and calcium ions. The flywheel riding on top of this that does the initial buffering is carbonate compensation in the ocean. That's this reaction that you see down here. It's an acid-base reaction. It's CO2 plus calcium carbonate goes to dissolved ions in solution. One of the, this room probably all knows this, but there's always diversity in audiences. So when you think about the carbon removal problem, or CCS, so many folks think about it as following the carbon atoms. It's not what the climate does, right? So the idea, right, is get your carbon gloves on, and they're like a carbon filter in some way, and you look around and you kind of grab hold of something, and now you're like, oh God, now I've got all this concentrated CO2, I'm just gonna go stuff it under the rug somewhere, or stick it in holes in the ground, right? It's not what the planet does. The planet runs an acid-base reaction. The perturbation to the natural cycle of excess burning of fossil fuels or of volcanoes going off is to the alkalinity cycle, to the acid-base balance of the ocean. And so that's what I'm trying to show here is carbonate compensation at work, that the surface of the ocean acidifies, the overturning circulation carries that acidified signal down to the bottom, and that acid interacts with the limestone, with the calcium carbonate shells of the plankton that have fallen from the surface, many of which are the foraminifera that Tim was showing us earlier this morning. Okay, so that's the natural one. This is why you haven't heard very much about it. Right? It takes tens of thousands of years, which is very quick, right, compared to silicate weathering and other things, but not so good on human timescales. And so we need to figure something out that mimics this antacid addition to the ocean, the title of the talk. This is like adding Tums to the ocean. We're going to try to solve this stomachache. Okay, so the accelerated version of this is called AWL because we're not very good at naming things. It's the accelerated weathering of limestone, right, is AWL. And it has been around in the literature since the late 90s. Rao and Caldera really pioneered saying, hey, why don't we just go mimic this reaction, right? This is nothing that we're doing by spinning out this company is all that new in this sense. They tried out a few different versions of it. They even thought about shipping briefly. The two big criticisms, and they're totally legitimate criticisms, were, well, we don't actually understand, and this is embarrassing as a field, right, that we didn't understand the fundamental kinetics of the dissolution rate of calcium carbonate in the ocean. We couldn't tell you how quickly a coral was going to dissolve given ocean acidification. That's why Will Burleson and I got started on this project decades, longer than I'd like to say, I guess, ago. We were just embarrassed as chemical oceanographers and low temperature geochemists that we didn't know this sort of fundamental rate law. And the other big problem with this is that the amount of carbon that you can sequester by AWL is directly proportional to the amount of water that you can move. And pumping water uphill is expensive and comes with a carbon footprint, and you quickly undo the benefit that you're doing. I'll show you two pieces of this quickly of what we've done about both of these parts. The first is work in the lab, and the second is shipping. Here's the state of our understanding of the rate of dissolution in the ocean when we got started over 10 years ago or so. This is a log plot, log on the y-axis there of a true flux mass per area per time over a factor of 1 million, right? That's 6 orders of magnitude there. And then the undersaturation is on the x-axis, phrased in a way so that you can't understand what we're talking about, so you can't come and take my job because I've made it too confusing for you to see what's happening. It's really relatively straightforward, though. Omega is a statement of the thermodynamics, and so 10 to the minus 2 here is 1% undersaturated. 10 to the minus 1, or halfway across the diagram, is 10% undersaturated, and all the way over to the right is sort of infinitely undersaturated. So you get more acidic moving from left to right, close to equilibrium on the left. And these were 4 different votes in the literature, seawater and freshwater, for what the dissolution rate was like as a function of the undersaturation. This is where most of the ocean lies. At its heart, this was the problem. Turns out all of that data is really good. I'm going to show you that those folks actually got it all right, but the interpretation was always messed up by trying to extrapolate to 0, 0. You were making measurements very far away from where the ocean actually sat, and so you made some assumption about what the rate law should look like. And it was written down this way: rate was equal to some k times this undersaturation raised to an n. These, in the end, they had like good arguments for why you would put these in, but fundamentally they ended up being fudge factors. And n here is varying, between 1 and 4.5, and k was varying in the literature by well over 10 to the 3. Really, that's what I meant by embarrassing. It's Caltech, so we're going to use isotopes to come up with some trick to try to figure out how to do this, right? Because it's sort of like you sign, and if you sign up for a job, you say, I'm going to use isotopes. What we did was we purely labeled C13 solid, and we put it into a bag with no headspace, and made the bag a little bit acidic or a lot acidic, or many times not acidic enough at all, and it was actually supersaturated, and measured the C13-C12 ratio of DIC over time. That's what you see over on the right. And so in something close to equilibrium, that's that shallow slope that you see on the one over on the right, not very much C13 comes into the solution over time. But far away from equilibrium, you're dissolving quickly, then you get very steep lines. So the slope of these lines are the rates. It's really a very straightforward way to just go and directly measure the rate. And so we did that a lot, right? Each one of these points is like a week of John Navio's time, measuring at different temperatures. And one of the cool things, I've already put the sort of helpfully put on those straight lines, was that there were breaks in the slopes, in the relationship between rate and undersaturation. At different temperatures, they always happened at the same undersaturation. We noticed this before we understood this, for longer than I'd also like to admit. I think we now understand it, but this was like one of those, wow, that's cool, I don't know what's going on, right? Like, why is this actually happening? But it immediately tells you something, right? There's also, it's a little harder to see because it's very hard to get the system to be close to equilibrium, but there's there's a second break in slope, a third set of lines in here. And what that means is that exponent n is a function of the saturation itself. And so if we come back and put that data back onto the exact same diagram I was showing you before, first of all, now we're filling in, now we're actually doing experiments in a lab that are like what is actually out there in the ocean, and n is changing with saturation state. So we noticed that too, and we also couldn't explain that, right? Until we read Patricia Dove's papers. And really she did an amazing job of looking at quartz dissolution, of all things, in a PNAS paper in 2005. And she did this great theoretical argument that said, what if you took classic nucleation theory for how you precipitate solids and flip it on its head and just say, we're gonna use the same energetic arguments, but for dissolution. And what's super cool about that is that for supersaturation, right, you can be a little bit supersaturated or you can be 1.2 or 3 or 10 or infinity, like you have this huge range of supersaturation states. For dissolution, you can only vary between 0 and 1. And so there are only 3 ways to dissolve the surface. Close to equilibrium, you pluck off individual unit cells that are already almost completely dissolved, that you see over here on the left. A step edge retreats. Get a little more undersaturated, have more free energy available from the solution, you can start to pluck out etch pits at the surface in places that are already stressed on the solid, in defects in the solid, and then go very far from equilibrium where you have a lot of free energy available from the solution, and now you can pluck out etch pits homogeneously from the surface. Every time you do that, you now make 4 new step edges. That's the fastest you can dissolve. Those are the breaks in slope. That's what these are. This has turned out to be super fun from just like an atomistic physical chemistry point of view. We've done a lot of work on that. I'm not going to show you any more of it here. It's been just like a gift that keeps on giving. We've done it in the water column, we've done it in the sediments. But now that we understand the dissolution rate, can we come back to this problem? We've checked off one of the 2 things about AWL. We now think we could go design chemical reactors and predict how well they would dissolve calcium carbonate in seawater. What about moving the water? Okay, so it turns out ships are just an amazing match with the technology for a couple of reasons. They are little floating power plants, right? They're like a power plant that's burning natural gas to give us electricity on land. In this case, they're just turning a big propeller, and it's not natural gas, it's HFO. It's like the craziest stuff that you can imagine. It's a solid at room temperature, right? The fuel that they put through. You guys all know this, oceanographers. It's 5% CO2 in the flue gas, right? It's concentrated CO2. The ship's forward motion is the water pump. That might be the only insight that Calcaria had that was kind of newish, right? Is that if you open up holes in the hull, the forward motion of the ship gives you your water flux. And that really lowers costs. We don't have to capture and compress and purify the carbon anymore. And we don't have to run massive pumps. The ship is doing it for us already. Okay. And so we make slightly saltier water from CO2, limestone, and seawater. That meant we had to start building things, and I had to try to become a chemical oceanographer, becoming a chemical engineer. That's landed us with building large prototypes down at the Port of LA and parking lot at USC. There are two different flavors of them. Maybe the most important part for this audience about these is that we can measure our inputs and outputs in real time. So our MRV, how much carbon we've actually sequestered, is a measurement, not a model. I won't show you, I would love to show you some sort of data model comparisons, my favorite ALK-DIC plots. I just want to say two other things quickly. The first is we've used the MIT GCM to try to understand the chemical impacts side of this. It's important to understand the ecological impacts part. That's ongoing work by others. But in the lower right-hand corner, that's the surface pH change 10 years on, doing our system on all the ships on the run from Shanghai to LA at steady state. The max number there is 0.01. We're adding pre-equilibrated carbon back to the ocean. When you add bicarbonate back to the ocean, you don't change the pH very much. Okay, there's a great story behind that last slide on that ships have just put a global carbon tax on themselves. I'll leave you with this slide where I think that ships actually could become a great way to take a larger chunk of CO2 out of the coming carbon economy. Instead of storing underground, we would store CO2 in the ocean as bicarbonate. That's sort of chapter 2 of Calcarea. I look forward to the panel afterwards and taking your questions. Thanks so much.
Thanks, Jesse. Sorry, we forgot to set the proper context for this section, of course, of the program. This is the present section, thinking about the future. And so we've heard from Jo Ellen, who's talked about the ocean's role. We heard about what Jess is doing now in terms of taking carbon out. And we're going to hear from David Ho, who's a professor at the University of Hawaii. And he's been, I used to think of him as a cycling climate scientist, but I know he's more than that now. And he'll talk to you today about MRV as well.
Okay, it's kind of hard to follow Jo Ellen and Jess, but I'll try. So I don't have the long history with Margaret that many of you have, but she and I are social media buddies. And you and I could be social media buddies too if you join Blue Sky. Okay. So in addition to being a professor at University of Hawaii, I am a co-founder of this organization, this nonprofit research organization called Seaworthy. There are now 15 of us. We're mostly funded by philanthropy with a little federal government funding. And what we are doing is building open source tools to verify that ocean-based carbon dioxide removal is actually happening. Okay. And we do this by building these tools and making them available on GitHub, but we also conduct field trials to generate data for verifying our models. And we are also working on methods to speed up these models, right, to make them more efficient or not to have to use the models at all because there's a carbon cost there. And we're also doing some field building. Okay, so that's a little about Seaworthy. So one thing I want you to think about is, so here's a plot of global CO2 emissions just from industrial uses. So no land use, right? And we're currently emitting close to 40 billion tons of CO2 every year. And the color bars that you see there, so we're at the red dot up there. And the color bars that you see is how much CO2 emissions dropped during COVID, during the lockdowns. So if CO2 emissions keep dropping every year from now until the end of 2030, the same way they did during COVID, we still won't reach this target of 20 billion tons of CO2 emissions every year by 2030. And that's to keep under 1.5 degrees, right? I mean, despite what Trump is doing to our economy, that's not going to happen. Now, when Twitter was still a thing, I proposed that we think about carbon dioxide removal as a time machine, because people don't understand orders of magnitude, right? The difference between 1,000, million, billions. So I said, what if we think about carbon dioxide removal as a time machine that takes you back to an atmosphere you had in the past? And then some Nature editors suggested that I say the same thing in a more dignified setting. So maybe some of you have read that piece. So this is the way we can think about it, right? So we know that in Iceland, they have this direct air capture system that's designed to remove 4,000 tons of CO2 a year. Before, our government got destroyed, the DOE had tried to set up these direct air capture hubs with the goal of removing 1 million tons of CO2 every year. And then these two companies, H&M and Salesforce, both multi-billion-dollar companies, like every year they make a lot of money. H&M proposed to buy 10,000 tons of CO2 removal, and Salesforce was going to plant 100 million trees. So what does that mean? I mean, these sound like a lot, right? So 4,000 tons is 3 seconds, 10,000 tons is 8 seconds, right, in a year. And then meanwhile, we've emitted another year's worth of CO2. And this is 13 minutes. So this is an investment of $3.5 billion, right, to remove 13 minutes worth of CO2 emissions. 100 million trees is about half an hour. So it's not a lot, right? Right now, when we're emitting 40 billion tons, over 40 billion tons every year, it doesn't take you back very far. But if we get to 15% of current emissions, like Jess was suggesting, in the future with our residual emissions, then it's more effective. Okay, so in terms of how much capacity we actually have, this is from something called the State of CDR report. And what it shows here is that most of the carbon dioxide removal is from what they call conventional CDR, which is basically forestry, right? And then there's this tiny little sliver that's considered novel CDR, and that includes something called bioenergy with carbon capture and storage. Basically, you burn biomass and capture the CO2, right? Or biochar, basically pyrogenic carbon, which they both use a lot of land because you got to grow the vegetation. So that accounts for, less than 1% of the total, but that's still the majority of novel CDR. And then the methods that are considered permanent, like enhanced rock weathering or some of the ocean methods, those are less than 0.05%. So right now we have no capacity, basically, for CDR. And so, actually, let's skip that. So why are we thinking about marine CDR, right? Which is sort of my focus. It's because, well, let's say we want to do CDR, and right now there's a lot of focus on stuff that's done on land, right? Or there's focus on direct air capture, which uses a lot of energy. But we know that on land, we use most of our land for agriculture, so there's the competition with that. And then also, when you do CDR on land, you have to think about where to put that carbon. Whereas in the ocean, because bicarbonate has such a long lifetime in the ocean, already there's a sink for it. So, and then, there's not the same competition for agriculture area. And I think the major reason why people think about using the ocean, it's like, that kid story, give a mouse a cookie, right? The ocean's already doing a lot, so we think, oh, let's get it to do more, right? So it's already taking up a quarter of our current emissions, and of the active carbon reservoirs, it's the largest one by far, right? And it's also a huge contactor. Like, there's a huge surface for exchange with the atmosphere. And I think those are really the major reasons. And so the way to understand marine carbon dioxide removal is that it's a two-step process, right? The first step is you do something to the ocean to reduce the partial pressure of CO2 in the ocean surface. But you haven't done anything for climate or the atmosphere in that step. And so the second step is either you equilibrate with the atmosphere, you take up CO2, and maybe you've benefited the climate, or that water subducts and it never touches the atmosphere and you haven't done anything. And to figure out which scenario happens or somewhere in between is important, right? And that's where MRV comes in. You've heard this term before. I'll get into it a little bit more. There are different categories of MCDR. Either people say conventional or novel, biotic, abiotic, photosynthesis, geochemical, technical, or nature-based or not nature-based. And so Laurent Bob and I made this horrible-looking diagram to try to reconcile all these different methods and where they belong. So in black are the different methods. But basically, you can think of them as I think, biotic or abiotic. So of the biotic methods, here are a bunch of them. You can grow macroalgae or microalgae. So ocean iron fertilization would be microalgae. Artificial upwelling, which I didn't think anybody was considering, and then Dave Carl, one of my colleagues, says, well, I'm still thinking about it. So maybe he's the only one. And then blue carbon restoration is another one. So these are all utilizing photosynthesis, right? And then the abiotic methods basically are geochemical. So either we somehow increase the alkalinity of the ocean, or there's a method that some of our colleagues are pursuing, which personally I think it's a bit nuts, but it involves removing CO2 from the ocean, putting that water back, and then hoping the ocean will take up more CO2. But then you gotta do something with the CO2 that you get out of the ocean. The reason I think it's crazy is because the sort of holy grail of MCDR is to make bicarbonate, right? So this method turns bicarbonate into CO2, liberates it into CO2, and then you gotta count on somebody else to do something with it. And at least you think that this is just academics talking about these things. There's actually a growing industry of startups that are doing all these different methods, right? So on the bottom, I listed the different methods and then what stage they're in, right? Either lab, demo, or they're actually selling credits. And there's a database of MCDR credits sold. And you can see, so the details aren't important, but this column here is tons sold. This is how much they've sold. And you can multiply that number by at least 100, right? Because right now, the removal is at least $100 per ton, usually more. And then the column to the left of that is how much has been delivered. And I think Running Tide has a big number next to it, but I wouldn't believe that. But basically, nobody has really delivered anything. But this is an active area of money transacting, right? And this is as of this morning. Okay, so you've heard both Joellen and Jess use this term MRV. So what do we mean by MRV? And this is an article in Bloomberg, basically saying that this is what the carbon market cares about, is MRV, right? So MRV is monitoring, reporting, and verification. And for our purposes, it's really the monitoring that matters, because the other ones are just the market mechanisms. But the two requirements for MRV are additionality, how much extra carbon has been taken up, and for how long is that carbon kept out of the atmosphere. So that's about carbon. Now there's a debate about, well, what about the ecosystem impacts? So I know this is something that Lisa cares about a lot. And so people are talking about, well, maybe there's CMRV and EMRV, right? And so one way to look at it is, well, if you know, your particular method, you know, kills a bunch of stuff in the ocean, maybe that's a gating criteria. We don't do that, right? But it's still to be decided, you know, where that line is. MRV is really hard, which is why we formed Seaworthy. Why is it so hard? Well, the ocean is really big, right? And the signal to noise is very, very small. Like Joellen showed this model of air-sea CO2 exchange. We know the ocean takes up 10 billion tons of CO2 every year. These projects maybe will take up a few hundred to a few thousand. So on top of that huge signal, which would be noise for CDR companies, it's really hard to detect what they're actually doing. And you know, only in models do you get the counterfactual, right? We don't know what would have happened if we hadn't done something. And then, as we all know, there are still things about the ocean we don't understand. Otherwise, you know, Scripps and other institutions wouldn't exist. So just to demonstrate the large spatial temporal scales, this is from a study that we did where it doesn't matter which one you focus on, they're the same except injections at different seasons. And this runs over 15 years. But you can already see that after a few years, the perturbation, this is an injection of alkalinity, but the perturbation's all over, you know, the North Atlantic. There's just no way we're gonna be able to sample that, right? So from observations, we're not gonna be able to get at this problem. And we know that, you know, there's these scales from genes to ocean circulation. We're talking about 15 orders of magnitude. And in each of those, there are things that we don't understand. And that contributes to, you know, how hard this problem is. So there are uncertainties that we can deal with, right? If we are undersampling something, or if there are processes that we're not sampling, that we should be sampling, or, you know, if there's some conceptual understanding that we don't yet have, we can gain those understandings. But then there are these sort of chaotic dynamics that we just won't be able to get to. So one way forward is something that we've done here, which is, this is a demonstration of one method, which is ocean alkalinity enhancement. We put a pulse of alkalinity at one spot in the ocean. We simulate it as it spreads out and takes up CO2 to see how much total CO2 the ocean takes up. And we do this, you know, in all these boxes around the global ocean in different seasons, right? And then we end up with something like this. So from left to right are the different seasons. Top to bottom is after a year, 2 years, 4 years, 8 years, and 15 years. And the colors indicate how efficient those areas are. So red is more efficient, blue is less efficient. So we can pick out areas where this is better than other places. And we've sort of developed this tool with Carbon Plan where you can actually explore these data. You can click on any of these boxes and change the parameters and see, you know, how efficient these different ocean areas are. And that might be a tool for the future if we can, you know, the boxes are still quite big, right? So we got to get to smaller areas and be able to verify that that's, you know, the model is indeed correct. And there are questions that need to be asked about these different methods. So what I'm showing here are for the abiotic methods, right? So for the PCO2 drawdown and then the dispersal and uptake, there are a bunch of questions you can ask that need to be answered before we're certain about, you know, how effective these things are. I won't go through these. And the same thing with the dispersal part. And these are things that we as oceanographers can contribute to, right? Both in academia and outside of academia. And the thing to figure out, I think, is how many of these questions are super important, right? So on the bottom is plotted knowledge gaps. So to the right is stuff that we don't know, right? And then On the y-axis is how important these things are. On the bottom, not so important. On the top, important. And it's really the top right quadrant that we really care about, right? Stuff that we don't know that are important. But then to figure out what those things are should be our priority. So people ask me to write opinion pieces a lot these days. So somebody wanted me to say something about MCDR. And what I said was basically, we should basically act like CDR doesn't exist, right? But we should research it like we still care about 1.5, right? So we need to decarbonize. We should put as much of our effort into decarbonization as possible, but at the same time, research CDR. So this is my last slide. So I think the way forward is we need to develop MRV, right? This is super important. We need to assess, all these things, how effective the methods are, the side effects. And I think we don't talk about this in our community enough, the social acceptance, right? I mean, if you have a measles vaccine that parents won't let their children take, you're gonna have an outbreak, right? You gotta get people to be okay with it. And just in general, not just MCDR, but in general, which methods take the least amount of energy, water, land, resources, and I think David Victor's group is actually working on this. Really research how much CDR is actually possible, because in these integrated assessment models, they just crank it up to as high as they want it, right? These other things don't matter, and it's not just geophysics or the environment or technical things. There's the economic part of it, the social acceptance part, but also the regulatory part. So all of these things are important, and I think we need to keep those things in mind. Okay, thanks.
That's terrific, thanks. Let's all stay up here. Joellen, Jess, David, stay up here. We're going to bring Lisa Levin up, who's a professor of biological oceanography here, and also marine ecosystems, to talk about some of this from the perspective of the biosphere and the concerns of ecologists. And then we're going to have a panel conversation. But first, I want to give the floor to you, Lisa, to comment on what you just heard.
Okay, so I was told to introduce myself. I'm a professor emerita of biological oceanography here at Scripps. I know many of you, but not everybody. And my research interests include the ecology of marine ecosystems, especially on the seafloor, and the role of the environment in shaping these ecosystems and how humans influence these ecosystems. So all of these things actually come together in considering how marine carbon dioxide removal, when applied at scale, might affect the ocean and its ecosystems. And I was told not to show slides, but after 40 years of teaching from PowerPoint, it's pretty hard for me, so I need to use my notes. So you'll have to forgive me here. So my main message here is that the application of marine carbon dioxide removal technologies that David's just done a great job of telling us about, when they're applied at a scale that's sufficient to sequester gigatons of carbon dioxide, which is what we need to do to alter the environment, what we need to do, will unquestionably alter the ocean environment. So, and this is true of the technologies you've heard about, ocean alkalinity enhancement and the ship capture, but also direct ocean capture and the different biological processes like ocean fertilization and biomass sinking. David showed some illustrations of these. And I will acknowledge that the effects on ecosystems have to be weighed against the negative impacts of climate change itself and the extent to which the mitigation activities to which MCDR would actually ameliorate climate change. So this is what we're balancing, effects on the ocean versus effects on the climate and improving the ocean for those ecosystems. And this is not an easy problem.
So I have like 4 main points to make. The first is that understanding and modeling the ecological consequences of MCDR is very complex, and it challenges our current state of knowledge. Most biogeochemical models don't represent these effects, especially at the seafloor. This is especially true for the deep ocean, where we're still learning about novel biodiversity and ecosystem functions and the services that this biodiversity underpins, including for the carbon cycle. We have tremendous opportunities for ocean science to contribute to this challenge in adaptation of existing observing programs, both in the ocean and satellite-based, in developing new sensors and platforms that can both provide needed baseline data in advance of MCDR application and that can detect the changes during and after MCDR testing and application. And I would say also ocean exploration actually has a critical role to play. We have a tendency with our resource extraction in the ocean, things like oil and gas drilling and potentially mining, that we act without knowing much about the ecosystems that are going to be affected. So we still have to go explore and understand what it is that we're going to affect. Okay. My second main point is that there's really only one ocean, and it's highly connected on many time scales. We know that daily vertical migrations of plankton mean that billions of animals at hundreds of meters depth move up to the surface every evening, and that they're going to experience whatever it is we're doing at the surface, whether it's ocean alkalinity enhancement or iron fertilization or whatever. We know that thermohaline circulation means that chemical alterations in the North Atlantic are going to affect the Pacific down the line 1,000 years from now. And in between those 2 time scales of every day and 1,000 years, we have subduction and upwelling and animal migrations across ocean basins happening. And all of these things link, all of these things draw amazing connections across the ocean. So for example, nutrient availability in the Southern Ocean, which we might influence with MCDR, will affect productivity in the tropics. Or changes that we do in one part of the ocean will affect the breeding success of animals in a completely different side of an ocean basin, for example. So the high connectivity of the ocean means that actions we do within one jurisdiction can affect others. If we do it within one country's exclusive economic zones, as you saw from David's models, it can affect other exclusive economic zones, or it could affect international waters, which are the common heritage, and that biodiversity is the common heritage of mankind. Okay, my third main point is that environmental consequences, risk, and uncertainty have not been a central part of MCDR development to this point, and that these risks are the least studied for the non-biological approaches like ocean alkalinity enhancement and direct ocean carbon capture. We know that MCDR at scale will alter light and turbidity regimes in the ocean. They'll alter ocean chemistry, including oxygen and food supply and habitats in the ocean. Deep ocean animals are highly adapted to really specific conditions. They can live for hundreds to thousands of years. They can reproduce really slowly and recover very slowly from disturbance. Massive entrainment is a part of several of these MCDR technologies, direct ocean carbon capture and electrochemical OAE, and also maybe the ship capture methods we heard about. And this entrainment will cause mortality of plankton and larvae and fish. Some of the technologies that involve creation of new biomass and then sinking will smother life on the sea floor. And loss of marine life, or even impairment of marine life, could actually counteract some of the additionality of the carbon sequestration that's being sought through MCDR.
Thorough assessments of ecosystem impacts are really expensive, and depending on the findings, might actually act to impede the development of the technology and the businesses, and so nobody really wants to pay for these. And these kinds of ecosystem assessments that we need are not really part of MRV, the MRV that David talked about. Although, as I said, it can be really affect the assessment of additionality. So I would like to suggest that we need ERF, environmental responses and feedbacks, to add to the MRV. So we have MRV ERF to enable an accurate cost-benefit analysis for each of these proposed technologies. And this is really necessary for society and decision makers to move forward and to help us understand how to avoid, or reduce, and mitigate the impacts of these MCDR technologies as we scale up. And then my fourth and last point is, beyond the cost-benefit analysis, there's a need for equity evaluation of who's going to benefit and who's going to pay the price of these technologies. For example, from any resulting environmental degradation that could happen. And this is where we get to the social implications of effects on people's livelihoods. So we are really challenged to consider all the stakeholders, including indigenous people of the world who have special spiritual connections to the ocean, which many people don't think about. So I guess my parting comment is, about saving the world, because that's what a lot of our presentations have been about, is that saving the world also involves not destroying the world we have and the carbon cycle services that that ocean world provides. So I'll stop there. Thanks.
My name is David Victor. I'm a professor here. I'm also at the Policy School and in Mechanical and Aerospace Engineering. And earlier, I was thanked for pulling all this together, but that's a complete fraud. The organizers of today pulled this together, and I was wondering who was really in charge. And when the introductory email to our whole panel went out, Kathy Constable jumped in immediately and said, "What are you going to do, and how are you going to organize this, and so on?" So I want to particularly thank you, Kathy, for getting us organized here. I mean, it's a credible team, and is a testimony to, with Dick Norris and others, a testimony to how Margaret brings people together. I just want to very briefly say something about my interaction with Margaret, because I'm here. I'm spending a growing fraction of my time here because of Margaret, and I want to thank you for that, the warm invitation. I didn't realize until lunch today that one of the themes was to share stories about traveling with Margaret and exposing her to danger. And so my danger story is, you may remember this, we had just visited a donor in Northern California raising funds actually for this kind of work. And I was feeling very proud that things seemed to be working very well. And we were flying in a small plane. I think it might have been at night, and the weather certainly was bad. And there was more ice on the wings than was normally my comfort level. So I don't think we were actually in any danger. But I will say that as I was looking at the situation, I'm thinking, boy, this would just be a major step backward for the field of research. So thank you very much for your persistence and patience. So we have, as is a testimony to the diversity of Margaret's interests and her mind, we have 25 minutes, 4 panelists, to talk about how we're going to use oceans to save the planet. And I've got 5 themes of things that I'd like to talk about. We live in inflationary times, so 5 may become larger than that by the end of the panel. But I first want to start with Lisa's comments, because I think the only way that carbon removal involving the oceans is relevant to fixing the climate problem is if it's done at scale. And intrinsic to that is that there are going to be all kinds of other impacts. And so maybe I could start with you, Joanne. You understand a lot about what's happening here and how this field is evolving, and then you've also been involved in this extraordinary Science Moms enterprise. And those of you who have not seen this, there's a lot online, and they're phenomenal ads, and they've been very, very effective. And I'm just curious, how do you grapple with this issue that Lisa has raised, which is that intrinsically carbon removal at scale is going to cause all kinds of side effects, and I think David Ho mentioned in passing, it's just like the wisdom of being vaccinated against the measles. Well, last time I checked, that wisdom is not spreading to everyone. So what's your thinking about how this whole field doesn't blow itself up on the launch pad by not taking seriously the kinds of things that Lisa raised?
We can do it. I came to Arizona when it was just a big red state full of wingnuts. I say that because I love them.
By the way, I grew up in Arizona, so just be a little cautious about how much you say.
Even our Republican governors are now understanding and pushing for FEMA to recognize heat waves as unnatural, human-made disasters. They don't support those sorts of things. So cooling centers, when we're trying to get all our old folks and folks, we didn't even have laws that said you can't turn people's AC off in the middle of a heat wave until recently. This is a really big deal. It's an adaptation that's crushing. And for us, we now understand that as goes the oceans, so goes our survival in the desert. That's not a joke. It's literally how much mixing the ocean does is essential. So what I'm worried about is not just the direct impacts of MCDR or other techniques, but straight up, does everybody understand that we are headed for a warmer, wilder, windier world? Not just a warmer world, but one where we should be burying our power lines. We should be working, and that's expensive. And it's mile by mile in every individual community. Are you ready for the size of the hurricanes that are going to hit? Are you ready for the kinds of inundation, permanent transition from okay to not? How about Black's Beach? How much of that bluff do you want to lose? So I think what we think of as natural change is going to be so extreme that I'm worried you won't even notice the impacts from MCDR.
So can I just quickly ask if David or Jess have views about this? Because I specifically am interested in this question of the ecological side of this. I think when folks talk about equipping a large fraction of the global shipping fleet with a bunch of devices that do something to the ocean or sprinkle stuff in the ocean, some of them get a little freaked out. How do you de-freak them?
Well, I think absolutely being freaked out is a perfectly fine first reaction. Like, our track record as humans on intervening in the climate or the natural world is just riddled with unintended consequences. So the social political license to operate is at the top of the most important list for Calcarea or for any of the ones that are out there, period. Like that, that's the first answer. I think though when we say throwing things into the ocean or doing things like this, I think the thing itself actually matters. Like we can't just lump all of them in together. Straight base addition to the ocean is not the same thing as reacting the CO2 with limestone before putting it back into the ocean. And if we start doing that, then we're gonna have a social political license problem with uninformed society. And that's just not fair. So if we're going to go after this problem, let's talk about the individual things and what they individually may or may not do.
So one of the individual things, and I want to go to David Hub with this question, one of the individual things is about permanence and verification, or monitoring and verification. So Jess said it's easy because it's an accounting problem. You said it's hard. That's because you're looking at a variety of different methods. And so I'm just curious, how is you're now in this space on a regular basis, working with all these different kinds of startups and so on. What do you see as the practical effect about this social license to operate, about some of the technologies that are actually very hard to establish what the net effect is going to be, and to be confident that that net effect is going to happen?
So if you're talking about startups, I don't think they care. And that's the honest truth, right? I think they're there to develop IP and then to sell themselves to a company, maybe a fossil fuel company that will buy them. And I'm not saying that that's a good thing, but we saw that with Carbon Engineering and Oxy, and I think all the CDR companies out there are saying, we want to be the next ones, right? And so I think it's up to the rest of us to say, you know, it's important that we consider all these things, including, you know, social acceptance. But so, you know, to get back to Lisa's point, I think she's right that, you know, on this sort of large deployment scale, we really have to think about, you know, the impacts on ecosystems and environment and people. But I think we're very far from that happening. We're very far from deployment, you know, like decades. And so I think that we should take the time that we have now, between now and maybe 30 years from now, to figure out those things. And that's where, you know, our community has a role to play.
Can I ask maybe Lisa to just follow up on that, then I want to shift gears a little bit. Are you comfortable with the idea that there's a bunch of startups and they're kind of doing what startups do? David called them crazy. In Silicon Valley, crazy is also known as a business plan. And so they're out doing things. Are there parts of this that even at these smaller scales give you pause when you think about how this industry may unfold?
Well, the part that gives me pause is what I already said, is that how do we mobilize to study the ecosystem consequences? Because the startups don't want to pay for this. It's not going to benefit them for the most part if we find negative impacts, which, you know, I'm not concerned about research and the negative impacts of research, because these are small scale studies and, you know, small field testing. But I think that we are truly challenged in figuring out who is going to study the ecosystem consequences. And it's going to be up to academia if we survive, you know, the next few years to do this ourselves, because I don't see the businesses doing it. And I agree with David that I don't think they even care if they can't sequester enough carbon to change the climate, as long as there's some IP that can get sold and make some money. So
My worry is that we're gonna actually see a problem with being Debbie Downers because we're trying to stamp out greenwashing. Meaning there's a real monetary interest in selling things that don't work. P.T. Barnum, a sucker born every minute, right? Greenwashing is everywhere. And we're the hardcore MRV experts who can say, won't work, will be damaging, won't work and is damaging, or might work, is working, wow, let's do it. And the problem is that there's a whole lot more of won't work, is terrible, oh my God, compared to something really serious like the things that Jess is doing. There's a big difference, and we're not great communicators. We kind of suck at it as scientists. We are just kind of generally terrible, and we're seeing the backlash of that right now. We have not convinced the American people and taxpayers that the academic enterprise, that science is worth their time and their money. No, seriously, we're up against it right now, and I'm terrified that we just have not done this. And I say that in front of Margaret, who's been fighting the good fight, and Rick, who's been, you know, out there communicating at the top of their lungs, but so far, it's just getting worse.
Jess, did you want to comment on this? I want to ask you a question about carbon credits.
Yeah, let's see, two comments, one quite quick. There are a couple of things that have been said so far that are just not true. I know of half a dozen carbon removal companies that are paying for ecological impacts of what they're doing. So just stop saying it, including Calcaria. But go look at Planetary, right? And Halifax. The whole people of Halifax got behind Planetary doing a scale in their harbor. A huge chunk of that was what are the ecological impacts of what's going on. So we have to just stop saying things that aren't true. I think that's maybe the first thing. The second thing is, I think it's super important to think about what role academics has to play relative to quote unquote startups coming out. Calcaria is a startup that came out of academics. We haven't kind of forgotten where we came from. I think it's super important at the same time that we're worried about what unintended consequences are we going to do, we also worry about, is the sign even right for the CO2 change, right? There's this dynamic that's developed when this was the energy transition, right? That the engineers in academics spun out companies to go after solar, wind, hydro, right? And develop new technologies that might work. And that's great. There's a pre-existing path there for communication back and forth between engineering PhD students who come there never intending to get a PhD because they want to sign up with a startup to get going. Now we're taking on the methane and carbon cycles. Those are system scale things at the planetary scale that I think you guys have done a nice job, as we all know, are a different problem than a technological one. And they're missing earth scientists. They're missing oceanographers out there to help them understand how are you doing it right, and how are you, you're gonna make the CO2 problem worse. I get pitched all the time for people who wanna grow coccoliths in the ocean. That will increase atmospheric CO2, right? So we need the earth scientists to be more engaged, not less engaged, with whatever these startup activities are, so that we get this thing right, not just from its ecological impacts, but actually for the sign of the CO2 change as well.
I mean, this is the very powerful case for some kind of an arrangement that involves private funding and startups and a whole American-style ecosystem, along with public interest, larger academic research of the type that we do here and do this in some kind of consortium. I want to ask about concerns that folks are having as some of these technologies go out to the marketplace. David, you showed in your talk a chart of all the tons sold, not as many delivered. Big difference between the two. I'm just curious as to what you're seeing about this as a major motivator for investment in this area. Because the whole carbon market world went through this period of selling, I think the technical term is garbage, very low quality credits that were greenwashing. And now you have a lot of interest and money behind higher quality credits, but a tremendous variation in the extent to which one can be confident that if you actually do this in the oceans or some other place, that it actually removes carbon. Are you seeing, in the folks that are working with you, are you seeing a variation in the extent to which these different technologies are viable because they can confidently say this is we know how much carbon is going to be absorbed? Because some of the work you showed is, maybe we know the sign in some of those cases, but there's a lot of uncertainty.
Yeah, I don't think you can systematically go through and say, these credits were bought because, we have confidence in that. It's because right now it's really individual companies doing their own due diligence, right? So there's this consortium Frontier that, does a lot of that, and then Microsoft, they also do their own due diligence. And I think more than anything else, it signifies how desperate they are for, some sort of permanent or durable carbon removal. And that they're willing to say, well, we'll see in the future whether this pans out or not.
So Microsoft, Stripe, handful of the other big tech companies, Apple and so on, have been willing to, Google, Alphabet, even Meta, the list goes on and on from there. Some of them have been willing to make big commitments, but they're super worried about the greenwashing problem here. And so therefore they're in some sense willing to overpay as long as they're confident about the quality here. And I guess the question to all of you is, does that mean that this industry of marine carbon dioxide removal, are you allies or are you enemies of all the other carbon dioxide removal technologies that are making similar claims? I mean, we've seen one big exit, which is carbon engineering. That's a direct air capture machine, so that's a land-based machine, exit to Occidental, to a petroleum company. We'll see other exits, but we haven't yet seen it on the marine side. So I'm just curious as to how we should think about how this industry unfolds over time.
I'm not sure how much I should say. I mean, I have a prediction.
You should say a lot, and it should be truthful.
Yeah. Well, I'm truthful about my opinions, I guess. I mean, so the former CEO of Carbon Engineering is now the CEO of Captura, which is this startup that spun out of Caltech. And they're doing direct ocean removal. They're doing the crazy method that I was talking about. And they are working with ExxonMobil. And I can very well see that, you know, at some point ExxonMobil might buy them, right? And I don't think that looks good for marine CDR, because you don't want to get bought for greenwashing purposes. And
Yeah, I'm trying to separate the specific and the general. So we've been very worried about the greenwashing label at Calcarea. Have had opportunity to take oil industry money, and for this exact reason, it's not worth it because you're shooting yourself in the foot to get to tomorrow, because you're running out of money, to not be able to get down the road because you're contaminated. And you're contaminated for very good reason, right? It's the same industry lobbyist as the tobacco industry that went behind fossil fuels. I'd like to switch back a little bit just to shipping, because so far what you've been talking about with Microsoft and Stripe and is what's called the voluntary market, right? It is company, and that's why the greenwashing thing comes along. There are regulated markets for CO2 already. The European Union has the emissions trading system, and it's you have to buy allocations against your emissions, and every year your ledger has to add up to zero. Shipping was pulled into that in January of 2024. An amazing thing happened 3 weeks ago in shipping, is that they decided to make that international, right? They decided to vote an actual regulated market globally on a single industry. And they voted it on themselves, right? Under pressure from the current American administration. I think this is an amazing example of mutualism, multilateralism, right? So like, just let me walk you through the story just for a second, right? So there's all sorts of acronyms, but the committee that is the subcommittee of the International Maritime Organization, the International Maritime Organization is the secretariat for the London Convention and the London Protocol. It's their job to make the rules, to follow those international rules outside of the exclusive economic zones. They have a standing subcommittee that worries about the environment of the ocean. That's where the job of figuring out what to do about CO2 emissions has landed. They meet every 6 months. The one last month, everybody was on sort of the edge of their seats because they said there's been enough talk and enough talk. Now they're actually going to do something. They're going to make a decision about what to do. It opens in London on a Monday. They say, okay, here are the sort of basic ideas that are on the table. We have a week. Let's see what we can do. On Tuesday, the U.S. administration pulls the U.S. delegation. IMO is one country, one vote, right? And so the Marshall Islands has the same vote as the U.S. As you can imagine, it's an incredibly political organization because of that. That's on Tuesday. On Wednesday, the current president writes a letter to every single country in the room, threatening them with retribution if they vote for this thing. They say, we don't like this Paris Accord. We don't like countries getting together. We don't believe in climate change. And on Friday, they vote for the tax. It's incredible, right? There's chaos generation everywhere in this country. And in academics, in the news in the last week, it is truly existential and worrying, right? There is hope out there, right? There's actually people still acting in our own best interest to do something about climate. Let's go support them.
So I want to say one more thing about the shipping example, which is, first of all, we are moving into this world, kind of fragmented, chaotic world. That's not a world where nothing happens. It's a world where you need a different strategy, and we see the beginnings of this. We have had the capacity to unify many other countries, including Australia, the electorates in Australia and Canada.
They're just going to leave the U.S. behind.
And shipping has this extra advantage, which is that the industry is highly concentrated, at least the container part of it. So you've got one firm, Maersk, which is highly influential in the business, and they're highly motivated to do something about it because they're based in Europe. So I think we're going to start to see more progress like this. But the question I want to put back, just mindful of the time, we've got 2 minutes. Just mindful of the time. We've been talking about this almost entirely as an American set of technologies. Are you seeing pressures in other parts of the world to develop the same kinds of technologies, leaving us behind? David?
I don't know about leaving us behind, but there are certainly startups in other countries like the Netherlands and Israel. And the UK is doing some stuff, so yeah.
Do you worry, Lisa, about the capacity of the international system to hold together the research enterprise needed to understand the broader ecological impacts of this?
Yeah. I mean, I do. I mean, the governance of MCDR is difficult, fragmented, involves internationally the London Convention and Protocol. There are moratorium by the Convention on Biological Diversity on everything that's not research. And then there are, I don't know how many countries have exclusive economic zones, 160 something or maybe more, and every government regulates its own waters, and that's fragmented governance as well for each of these applications, and we need something more coherent to help the world pull together.
Can I just close then, just as we finish up, Jolyn, with a science question. You in your talk, this terrific implications of the terrific observations about how it gets windier, it affects upwelling, it's going to affect all of David's models, it's going to affect some of these business models, or at least some of them, because of the contactor issue. Do you think the error bars in the way we understand some of these technologies are getting bigger over time the more we learn about this, or getting smaller?
I actually think there is an incredible gap in the sort of market function at this point that should be filled by an academic organization. Really, what we need is the Good Housekeeping seal of approval. We don't just need, Rick used to advertise for a global carbon observatory that was going to be, NOAA plus other folks. And we just haven't seen that close on the international level. On the other hand, we have a lot of very, very clever academics, et cetera. And if they're not involved in a startup and they are interested in getting the word out about effective, well-run, interesting, possibly transformational technologies, companies, people, and impacts, we could be doing that. We have that kind of cred. We are capable of doing those sorts of evaluations. We normally think of it as a sort of National Academy level, since they have a charter signed by Abraham Lincoln to provide advice on science and technology policy in the public interest. But since they aren't doing it, there is a gap.
Yeah. It seems like these good seal of approval issues are going to be incredibly important for understanding the larger MRV context, especially for technologies which don't automatically have trivial monitoring problems, and notably for the larger ecological impacts, both because they're important and because they're going to affect social license. That's something that the classic academic enterprise in partnership with industry needs to do. I think it's gotten a little harder for this country to demonstrate credibility about that, but it's not impossible. We can make progress. Thank you all. We're going to break now for 15 minutes, and we're going to come back at 2:55 for the next talk. Thank you.